You're listening to Scientific Giants Who Changed Our Understanding of the World We Live in. Each episode stands beside one mind and follows a thread of curiosity until it ties to the world we inhabit. Today we climb a narrow stair in Cambridge, run a palm along a scarred table, and pause at a pinhole cut in a shutter that turns noon into a blade. On the table lies a prism, a small triangle of glass that to most hands would be a trinket for teasing color out of sunlight. In these hands, it becomes a witness. A beam slants in, strikes the glass, and falls on the opposite wall as a band of colors, edged cleanly enough that you can count where red surrenders to orange and where violet stops pretending to be blue. The man who set this up is young, intense, easily wounded, and immoderately patient. The room smells faintly of smoke and ground glass. He is Isaac Newton, and in this plain light he will teach a civilization to speak a new language, calculus for change, experiment for certainty, gravitation for cause, and he will train it to distrust even its most cherished comfort until a measurement has earned the right to be believed. He begins far from Cambridge, in a farmhouse at Woolsthorpe, in the winter of 1642 by the old calendar, 1643 by the new. He is small enough at birth that the women worry. His father is already dead. His mother will remarry and leave him for a time with grandparents who learn, quickly, that their slight boy is a poor farmer and a dangerous tinkerer. He carves sundials into walls and gateposts with a neat hand. He builds kites and machines with too many moving parts. He scribbles verses in lists of sins. He learns to hide anger in work. At the grammar school in Grantham, he lodges with an apothecary and discovers that a shop where powders are ground and liquids decanted is a better school than any room where boys repeat declensions. He comes to Cambridge at 18, unremarkable at first, then roused by the library. He copies pages of Descartes and Euclid into notebooks thick with his own annotations, reads Kepler's Optics with excitement and suspicion, and trains himself in secret to do mathematics at speed in the margins of other men's certainties. Then plague shuts the university, and he goes home. The years 1665 and 1666 will later be polished into miraculous, but what they really are is unmolested. He has a roof, a shutter, a prism, some paper, and time. He watches white light break into colors, then recombines those colors into white with a second prism, so that he can stop his own mind from insisting that the prism somehow paints the colors onto the light. When he narrows the beam and isolates a single hue with a slit, then sends that hue through a second prism and finds that it refuses to split further, he recognizes the clue that matters. Color is not a stain or a corruption light picks up. It is a property of light that a glass sorts by bending each hue differently. White is not purity. White is mixture. He writes it down in chilly sentences because the discovery is warmer than he can afford to be. He knows how reputation operates in small rooms, how a claim as sharp as this will invite a tone of polite denial from men who like their heavens and their sun unpunished. He builds a reflecting telescope to solve a practical problem. Refracting lenses, no matter how finely ground, spread colors and blur edges, and in so doing he discovers something about himself that the century will learn with him. He is most dangerous when a problem can be solved with brass and glass. He has also been teaching himself to write time in the language of change. The old arithmetic works on totals and distances. The new questions he wants to ask need rates and bends. How fast is a speed changing? What area builds up under a curve as time flows? If you send a point skittering along a curve, how does its direction lean and how much? He invents a private grammar for these questions, fluxions and fluents, dots over letters to show how a quantity swells moment by moment, series that do in the head what long sums did on slates, and he keeps the system mostly to himself. Writing notes that he files away with dates but not with instructions on how to read them. He is young and proud. He is shy and vain. He wants to be right more than he wants to be first, and he wants to be first more than he wants to be thanked. Out of this tangle will come the method of fluxions, the art we now call calculus, which will later be the subject of a quarrel that wastes years and changes nothing about how well the method works. He returns to Cambridge when the plague ebbs and is elected a Fellow of Trinity College, then, astonishingly young, to the Lucasian Chair of Mathematics, a post that pays poorly and demands lectures that he will deliver in a voice that carries only to the first few benches. He sends a paper to the Royal Society describing his little telescope, It delights the fellows because it is not a poem or a prophecy, but an instrument that can be held and tested. He follows with a paper on light and color. It lands like kindling in a room already warm with argument. Robert Hooke, a virtuoso of apparatus and a jealous guardian of his own reputations, distrusts the tone. Who is this provincial, making color so simple? Others reply with devices and words. Newton replies with more decisive arrangements that strangers can repeat. He learns the hard way that being right is not sufficient. You must also be careful whom you are right in front of. He withdraws, bruised and stubborn, and buries himself in the work that makes him least vulnerable. Mathematics that can be done without help, and experiments that need only his own hands. He is not alone in London, but he is apart. Hooke runs the Society's demonstrations with a rough charm. Boyle writes experiments with a gentleman's severity. Halley, young and generous, builds networks and keeps peace. Flamsteed watches the sky with a cataloger's devotion and wants his numbers treated with care. Newton reads their letters, answers when he has to, and learns to wait until someone else's need calls him out. That summons will come from Halley, and it will drag him from light into gravity. Imagine a small room in Cambridge again, years later, when Halley arrives with a question he has been carrying like a coin he cannot change. If a planet obeys Kepler's area law and distant sun, and if we take seriously the inverse square hunch whispering through the work of Hooke and Wren, what path would such a planet trace? And in reverse, if we see the planets trace ellipses with the sun at a focus, what central force law must be tugging to make that necessary? Halley asks. Newton answers, ridiculously, that he had done the problem long ago and misplaced the result. He promises to write it down. He does, first as a short tract. Then, under Halley's prodding and protection, Halley will pay for printing when the Society cannot. He expands the tract until it is a book that recasts natural philosophy as a profession with requirements. Definitions at the front door, lemmas and rules of reasoning along the hallway, propositions proved with that Euclidean calm that silences most rooms, and at the back, a view of the heavens and the tides, comets and procession, that makes even a prince feel small and safe at once. The book is the Philosophiae Naturalis Principia Mathematica, printed in 1687, known now simply as the Principia, and it is an instrument disguised as a text. It begins by telling the reader what words will mean: mass, quantity of motion, centripetal force, time, and by warning that time and space can be treated as absolute for the sake of calculation. A dangerous claim that he makes credible by the usefulness of what follows. He lays down 3 laws of motion that sound today like almost nothing, and therefore move everything. A body perseveres in its state of rest or of uniform motion, in a straight line, unless forced to change by impressed forces. Change in motion is proportional to the impressed force and takes place along the line of the force. Action and reaction are equal and opposite. He then shows, proposition by proposition, that if a central force pulls always toward a fixed point and strength falls with the square of the distance, planets must sweep out equal areas in equal times and must trace conic sections, ellipses if they are bound, parabolas or hyperbolas if they are on the run. He gives Euclid's geometry a new job, not only to decorate proofs, but to hold motion still long enough to see its skeleton. He writes with a style that is both generous and cruel. Generous because he gives his reader the tools needed before using them, even when the tools are hard. Cruel because he refuses to show the algebraic throat of his method and instead writes in the older geometric idiom, forcing anyone who would argue with him to learn his recent past and his ancient taste. He couches the calculus in lemmas about first and last ratios, a careful way of passing to limits that satisfies those frightened of the infinite, while coolly doing the work of infinitesimals. He proves that if no external torque acts, the area law is equivalent to the conservation of angular momentum. He derives the relation between period and radius that Kepler had heard as harmony. He calculates how an oblate spinning Earth bulges and makes the equator heavier. He explains, not just predicts, tides, aging them under the supervision of the moon, and shows that the lunar pole and the solar pole superpose, producing spring tides at new and full and weak neaps at quarters. He gives comets back their dignity by showing that their long-flung paths can be understood as conic sections too, not caprice, but geometry that cares less about prejudice than about initial conditions. In the Principia, he is not merely computing. He is redefining what counts as cause. A cause is not a story that pleases the ear. A cause is a rule that binds motion to measurable quantities. To say that the moon falls toward the earth is not poetry. It is a calculation checked against the rate at which a stone gains speed when dropped from a tower, and against the rate at which the earth's surface falls away from a tangent as you walk around it. He compares the per-second fall of an apple with the per-second fall of the moon toward the earth along its orbit, and finds the proportion that ties them together. Distance squared in the denominator, a law that lets you scale from orchard to orbit without sacrificing sanity. Then he extends, with a bravado disguised as modesty, that ratio to everything with mass everywhere. The sun pulls the planets, Jupiter pulls its moons, the earth pulls the tides and their basins. Two stones on a table tug one another so feebly that only experiment can make the whisper audible. The name for that rule is universal gravitation, and it behaves so well in the world that almost nobody in his century will be able to bear his restraint at the end of the book. Hypotheses non fingo, he writes, I frame no hypotheses about what gravity is, only what it does. He refuses to dress the law in a cause that would soothe metaphysicians. He insists on leaving the room with the rule standing naked, because clothed in cleverness it would be easier to wound. This severe refusal inflames his enemies and disappoints his friends. Philosophers trained to treat contact as the only honest cause accuse him of smuggling in occult qualities. Action at a distance looks too much like magic. Theologians itch to assign gravitation to a divine habit and wrap it in piety. He declines both. He does not say God is absent. He says the calculus of cause must be written without invoking intentions. He is building a republic in which a proof can win in a hostile city without a patron's escort. The irony is that he will spend immense portions of his life outside that republic, laboring in alchemy and theology on projects that do not belong in the Royal Society's minutes, and that he will not publish while he breathes. Even while he invents the most powerful natural philosophy yet written, he spends whole nights in a different workshop entirely, chasing the transmutation of metals in crucibles and retorts, copying recipes from manuscripts that smell of secrecy and the 17th century's appetite for the older world's whispers. He reads the prophets with a mathematician's severity and believes he can date the end of days by the book of Daniel and the measurements of the temple. He writes a vast chronology of ancient kingdoms, trying to reconcile secular histories with scripture by arguing the lengths of reigns and the honesty of eclipses reported by old scribes. He keeps these works private, or circulates them to a few, because he understands the way authority works. A wrong book can unmake the right one. He is not embarrassed by his alchemy and his prophecies. He simply knows that optics and gravitation are fragile enough to need the shelter of silence about everything that can be misquoted. He is capable of friendship and capable of making enemies out of friends. The letters to Hook carry that famous line about standing on the shoulders of giants, a line that reads like humility and that may conceal a small sting. He quarrels with Flamsteed, the astronomer royal, over access to star positions and treats the man cruelly in the editing room. He becomes president of the Royal Society in 1703 and presides with authority that sometimes looks like the vindication of his youth and sometimes like its revenge. He prosecutes counterfeiters as warden and then master of the mint with a zeal that would be called police work if the phrase existed yet, haunting taverns, recruiting informants, decoding lies, and he runs the great recoinage with a hard sense that money's value is public trust turned into metal and must be guarded as jealously as any theorem. He accepts a knighthood from the crown, sits for portraits whose props, books, prisms, and orrery show what power now looks like when it wants to flatter itself with science, and lives long enough to see the word Newtonian used as a token of authority that makes him uncomfortable because authority was the thing he meant to replace with method. He writes another great book, one as different from the Principia as a lens is from a lever. Optics appears in 1704, written not in Latin but in English, and it is a guide to an experimental life. He narrates his prism experiments with that dangerous clarity that invites emulation. He describes the reflecting telescope and the reasons it defeats color's mischief. He investigates thin films with a casual brilliance that becomes the famous Newton's rings, the bright and dark bands that play across a lens pressed lightly to glass, evidence for interference effects that he will stubbornly describe in corpuscular terms, even as wave language gathers other minds. He presents the color circle that painters and dyers will understand before philosophers do. And then, in the queries at the end, he becomes speculative in a way that is almost tender. He asks whether light may consist of particles with fits of easy reflection and transmission, whether ether fills space and carries forces, whether chemistry can be reduced to attractions and repulsions that make matter assemble and fall apart by rules not yet named. He does not assert. He asks. He does not mellow in age so much as he learns to leave room for a future he cannot write. He is also drawn into the fight he had hoped to avoid, the one that wears neither prism nor pendulum, but a badge labeled priority. Gottfried Wilhelm Leibniz, brilliant and courtly, publishes a calculus in proud symbols and teaches Europe to use it with a friendliness Newton never learned. Newton, who had invented his own version years earlier and kept it more private than was prudent, cannot bear the thought that the method might go down in memory under another man's name. He authorizes the Royal Society to investigate and then writes, anonymously, much of the report that decides for him. It is an ugly episode. It does not alter the fact that both men found the same continent from different beaches, and that, once found, the continent did not care whose flag a book tried to plant. The method works. It does not need a name. But men do, and Newton remains a man longer than he remains a method. His health is often poor. He eats little. He sleeps badly. He is not gentle when he thinks someone has tried to make him small. He is, nevertheless, generous to young workers who shiver with the same fever he knows. He tolerates, even encourages, the correction of the Principia where it needs it. Second and third editions appear with emendations and additions that make the work not a monument but a moving machine. He lets the moon's motion be recalculated with more terms, the precession of the equinoxes be retuned, the language of forces be sharpened. The book grows not by accretion but by discipline. It is the opposite of a collection of curiosities. It is a forcing garden in which only methods that survive the season are replanted. He is not a solitary genius in the sense that legends hawk. He thrives because a culture is building rooms for his kind of work. The Royal Society, for all its squabbles, is a place where instruments can be shown in public and claims be tested without asking a prince for permission. Universities, slow and suspicious, nevertheless supply rooms free of winter's wind, where a shutter can be pierced, water clocks tend, and lenses ground. Printers' shops learn to set diagrams with care and formulas with fewer errors. Postwriters carry letters and small parcels swiftly enough that a new measurement can be turned into a new conjecture before the urgency evaporates. He makes the most of these rooms and these writers. He will also, at times, use his power within them to settle scores he should have left alone. If you want the flavor of his mind in the hand, open Optics and read how he designs the experimentum crucis, the crucial arrangement that teaches the spectrum not to lie. He drills a small round hole into a window shutter to admit a narrow beam, inserts a prism to disperse it, cuts a slit in a second card to isolate a color, and passes that single color through a second prism to see whether it will split again. It will not. He then recombines the fan of colors with a lens and shows that white returns, not whiteness with a bruise of color still hiding in it, but white pure enough to abolish the accusation that the prism paints. Each step is designed to force a skeptical eye to surrender without humiliation. Each step is a kind of courtesy. Each step admits of failure, and thus their success is not a trick but a demonstration. If you want the flavor of his mind in the wrist, Drag a curling stone across a smooth ice and watch how, once pushed, it persists until a roughness or a slope or a wall forces it to confess. If the ice were perfect and the stone without friction, the stone would slide forever in a straight line. This is not a parable. It is an everyday apology for the first law, and it is absent from most life under the old physics because the world supplies friction as a birthright, and so sentimentalizes rest as more natural than motion. Newton does not sentimentalize. He tells us that nature keeps books. If motion continues, it is because nothing has drawn from its account. If motion bows, it is because a force has charged it a fee. If you want the flavor of his mind in the voice, listen to the rules of reasoning in philosophy near the beginning of Book 3 of the Principia. He enjoins us not to admit more causes than are sufficient to explain appearances, not to feign different causes for phenomena that are the same, to understand that qualities found everywhere in experiments are probably universal in all bodies, and to let propositions that are inductively true be held as exactly or very nearly true until new phenomena throw them into question. These rules are not laws, they are manners. He is writing a code of conduct for minds that would prefer to gossip. He is teaching us how to resist seductions, of authority, of analogy, of novelty. The hypothesis non fingo at the end is simply a stricter version of the same manners. What did he change beyond the contents of books? He changed the shape of persuasion. Before him, a philosopher could force assent by lineage and loftiness, by a tone of ancientness, by a fine Latin, by a name attached to an idea that suffered no experiment near it. After him, and because of him, the persuasive on earth is in the hands of those who can set up an arrangement, make a measurement, and show a calculation that a stranger can follow with the same numbers. He moved authority from pedigree to procedure. He made it honorable to write an experiment, and dishonorable to be clever without one. He changed what a university thought it had to teach to stay alive. Not only texts to be glossed, but methods to be imitated, apparatus to be carefully passed from hand to hand. He also changed, in a way he would not have allowed himself to say out loud, how we tell stories about ourselves. To say that the same law that pulls an apple down, pulls the moon around, and pulls the sea up against its coasts, is to say that our lives and the lives of the stars share grammar. It is not an insult to human meaning. It is a stern comfort. The world is not a series of compartments managed by local deities who cannot speak to one another. It is a place where a small calculation, done carefully enough, can calm a harbor and a mind. The cosmos becomes a room where you can be at home if you are willing to learn its rules. There is a scene, not in a lab but in an office, that also belongs to him. He sits as master of the mint, with reports of clipped coin, sweated coin hammered thinner and then passed at face value by men who pay the difference with their neighbor's hunger. He organizes the recall, not as a crusade, but as a computation. How many dies, how many presses, what alloy, what date, what penalty. He understands that value is a social measurement that lives inside metal, and that to keep that measurement honest, you must attach it to a process that frightens those who would lie. He prosecutes a gifted counterfeiter. William Challoner, by building a case the way he builds a proof, witnesses, documents, dates, cross-checks, and sees the man hanged. It is not a pleasant story. It is part of the same intelligence. Truth is not tender, and the public instruments that carry it, coins, clocks, tables, laws, are only as honest as the severity with which we keep them so. He grows old. The portraits grow heavier and the hair whiter. The expression in the eyes stays alert and a little proud. He presides over the Royal Society with a formality that keeps chaos at bay, and sometimes progress too. He is still capable of delight, the late letter that laughs at being made to sit for another portrait, the quiet admission that a correction is the right one. The way he toys with a prism like a man who is never tired of that first room, although delight is not the main mood. He is buried in Westminster Abbey beneath a Latin that tries to say what will not fit, that a man did for human understanding what no one else had done, and that his life offers more proof than any sermon that mind and method are an acceptable form of gratitude for being alive. If you stand now where he stood, in any small room with a shutter you can pierce and a surface you can mark, you can reproduce his work in miniature. You can split white. You can recombine. You can find a law of fall with a clock and a smooth plank. You can time a pendulum and feel the square root relation between length and period show its face. You can watch a spinning bucket's water climb the sides and feel, in your palm on the rope, the argument about absolute and relative motion begin again. You will not need his genius to do this. You will need only his manners. It is the best kind of legacy, the part that can be taught to anyone who wants to join. His shadow is large enough to be misused. For a long time, Newtonian will mean stern as much as right, and fields that do not yield to his kind of reasoning will be treated as suspect. Later revolutions will be read as rebellions against him. Relativity softening time and space, quantum theory disputing particles' obedience, chaos reminding us that sensitivity to initial conditions is not a moral defect, but a property of equations. These are not refutations. They are improvements done with the very manners he insisted on. To treat his laws as idols is to betray his method. He taught us to let a measurement overrule pride, pride included, to him, his own. When I try to hold him still in a single image, I fail, and the failure instructs. He is not any one of his rooms. He is not the prism alone, or the calculus alone, or the proof about a moon. He is the insistence that a mind put itself in the way of the world's honesty and then not flinch. He is the decision to publish under geometry, not because algebra is weak, but because geometry forces a certain chastity in the steps. He is the refusal to pretend that gravity's cause must be dressed in a familiar garment before its law is allowed to work. He is the bad friend who becomes a good president when an institution needs a spine. He is the good enemy who makes you better because his standards feel like an insult until they become your own. He is, in the fairest phrase, a builder of arrangements that make truth easier to see. He died in 1727, a virgin, the gossip says, as if a public indifference to romance should be laid at a mind's door as proof of its coldness. It seems a small insult to pay a man whose affections were spent on things that repay attention better than nearly anything else has. He left us not doctrines but devices, not slogans but steps. We can walk them or not. The world will not change its habits, only we will. You have been listening to Scientific Giants Who Changed Our Understanding of the World We Live in. Today we stood in shuttered rooms and under cathedral vaults, in a mint and on a harbor, beside a mathematician who put a geometry under motion and then insisted, sometimes gently, sometimes howlingly, that the rest of us learn to be as honest as our instruments. In our next episode, we will enter a Paris laboratory lit by oxygen's clear flame, where a tax collector with a gift for balances and names, Antoine Lavoisier, will weigh air, kill phlogiston for good, and give chemistry its conservation and its common tongue. Until then, thank you for your attention and your time. This episode was written as a continuous story for the ear. If it moved you, bring a friend along next time. Until our next hour together, keep an eye on the rules of reasoning you lean on. They are closer than they look.